Hey there, and welcome to The Explainer. Today, we are stepping into the shoes of a math detective. Your mission, should you choose to accept it, is to investigate the fascinating world of proportional relationships. We're cracking a specific case straight out of grade 7 pre-algebra today, and we'll be digging into the mathematical evidence to separate fact from fiction. By the time we're done here, you're going to be an absolute expert at spotting whether a relationship is truly proportional just by glancing at its data. So go ahead and grab your magnifying glass because we've got a mathematical mystery to solve. Here is a quick look at our investigation roadmap. We're going to look at two competing claims, analyze the data table, graph for the origin, build the math equation, identify the valid claim, and then we'll wrap things up with a student justification check. Section 1, two competing claims. Okay, let's dive into this. You know, every good investigation has to start with a set of suspects, right? Here, we've got two hypothetical student claims. Claim A is a geometric relationship based on a map scale. It says that 1 inch on a map equals exactly 5 miles in the real world. Simple enough. Then we have Claim B, which is a real-world pricing scenario. Think of a taxi fare, where they charge you a flat $4 just to get in the car, plus an additional $2 for every single mile you drive. Now, both of these are linear relationships, meaning they grow at a nice steady rate, but only one of them is a true proportional relationship. As our resident math detective, which one do you suspect is the real deal? Well, to find out for sure, we need to gather some hard evidence. Moving on to Section 2, analyzing the data table. A top-notch detective never relies on just a hunch, so let's start with the raw data. Take a real close look at this table. In that first column, we have our input, which we call X. This represents our inches on the map for Claim A and our miles driven for Claim B, and we're just looking at inputs of 1, 2, and 3. Now look over at the outputs, which we call Y. For Claim A, 1 inch gives us 5 miles, 2 gives us 10, and 3 gives us 15. For Claim B, 1 mile costs $6, 2 miles costs $8, and 3 miles cost $10. Okay, so both columns are definitely growing in a predictable way. But remember, we aren't just looking for growth here. We are hunting for a highly specific, kind of hidden pattern that actually defines proportionality. To find that hidden pattern, we need to use this definition right here, the constant of proportionality. In math, we use the letter K to represent this. It's basically the constant ratio between two proportional quantities. And you find it by simply taking the output, Y, and dividing it by the input, X. If a relationship is truly proportional, this calculation is going to give you the exact same number every single time. It's the ultimate test. Literally, if that ratio wobbles even a little bit, your suspect is out. It is not proportional. So let's actually apply that test to our data. For Claim A, we divide 5 by 1, which is 5. We divide 10 by 2, yep, that's 5. And we divide 15 by 3, which is also 5. So Claim A has a perfect constant ratio of 5. Now let's test Claim B. 6 divided by 1 is 6. But 8 divided by 2 is 4. And 10 divided by 3 is, well, it's 3.33 repeating. Wow, the ratio completely shifts. The actual cost per mile is changing, depending on how far you drive. I don't know about you, but this makes Claim B look highly, highly suspicious. Which brings us to Section 3, graphing for the origin. So we have our first major clue, but we really need to corroborate it visually. Whenever you look at a graph to check for a proportional relationship, you need to run through this crucial two-part visual checklist in your head. Step 1, is the graph a perfectly straight line? If it curves at all, it's out. Step 2, does the line pass exactly through the origin? The origin, of course, being the coordinate point 0, 0. Now, both of our claims will actually pass Step 1. They both create perfectly straight lines. But Step 2, well, that's where the truth comes out. Now, what's really interesting about this is how the real-world context of the taxi completely breaks our graphical rule. Just think about Claim B for a second. If you drive 0 miles, do you pay $0? No way. The taxi has that $4 starting fee just for opening the door and getting in. That means on a graph, its line starts at the coordinate point 0, 4. It completely misses the origin. Claim A, on the other hand, means 0 inches on a map equals 0 miles in real life. It passes perfectly through 0, 0. Let's head into Section 4, building the math equation. Let's translate our visual and numerical data into our third and final piece of evidence, equations. To do this right, we need to understand the anatomy of these equations. A purely proportional equation always looks like this, y equals kx. Notice that the only math happening there is multiplication. You take your input x, you multiply it by your constant rate k, and boom, you get your output. That's the whole shebang. A non-proportional linear equation, though, looks like y equals mx plus b. It has a constant rate being multiplied, but it also has a standalone starting value added or subtracted right at the end. A true proportional relationship never ever has that extra piece. Let's take a look at the actual math equations for our two claims. For claim A, the map scale, the equation is y equals 5x. It perfectly matches that pure y equals kx format we just talked about. For every inch, you just multiply by 5. Done. But for claim B, the taxi fare, the equation is cost equals 2 times the miles plus 4. That plus 4 is our starting value. It's our y-intercept. It matches the y equals mx plus b format to a t. And that proves mathematically that claim B is a linear function, for sure, but it is definitely not a proportional one. All right, section 5, identifying the valid claim. We've run the numbers, we've checked the visuals, and we've built the algebra. It's time to step back, look at the evidence board, and render our final verdict. So, math detectives, I want you to synthesize the 3 representations of data we just looked at. Between claim A, the map scale, and claim B, the taxi fare, which one actually survived the constant ratio test? Which one passed perfectly through the origin on the graph? And which one fit that strict y equals kx algebraic anatomy? Well, the crucial point here is that claim A is our clear winner. The map scale is the valid proportional relationship. I mean, the evidence is absolutely undeniable, right? In the table, every single pair of numbers gave us that perfect constant ratio of 5. On the graph, 0 inches meant 0 miles, meaning the line shot straight through the origin at 0, 0. And algebraically, it perfectly fit the y equals kx format as y equals 5x, with absolutely no standalone starting value tacked onto the end. The taxi fare was a totally great example of a linear relationship, but because of that pesky $4 starting fee, it completely failed the test for proportionality. And finally, section 6, student justification check. This brilliantly illustrates how the math connects across tables, graphs, and equations. But now, I'm putting the ball in your court. Imagine a scenario where a recipe requires exactly 3/4 of a cup of sugar for every single batch you bake. So, what do you think? Is this a proportional relationship? Now, don't just guess here. Create a data table, sketch a graph, or write out the equation. Look for that constant ratio, check for the origin, and see if it fits the anatomy we just discussed. Can you build an undeniable mathematical argument for it? Thank you so much for joining me on this investigation for the Explainer, and keep exploring the math all around you.